I will encourage you not to make it. I think are the exams available for pickup? Yes. So the exams, as soon as we announce the grades, they're pretty much available in the physics office, Brockman 201. Second floor Brockman, all the glass doors, all the friendly physics people wanting to talk to you, they have your exam. And they have your pledge problem, if you haven't picked that up either. All available for pickup. And you should pick up your exam and look at it and see why you got what score you got and strategize for the next exam. This is an announcement that just went up this morning. There was one multiple choice we're willing to regrade, but read the restrictions, okay? This is not open season on more or higher exam score. This is a very specific, we will look at these two, and if it was those two answers, we'll give you one more multiple choice. That's all it is. Okay, so read it, and it was just that one that was a little questionable about terminal block. Okay? All right, what we're doing today is we're moving on to energy. So I didn't want to write this again, but you may recall 2 weeks ago we started momentum. And we spent 2 weeks on momentum, and I said momentum is a different way to do physics. It's a different way to do motion problems. Rather than forces and detail kinematics, we have collisions and interactions. They're easier solved with momentum. And I told you there's a third one coming, and it starts today, and it's energy. And these are good for sort of initial, final problems, as you'll see. So we're about to spend 2 weeks on energy. That's the plan. That's what we're doing. All right. Now that can go away. Okay. Uh, 2 weeks on energy. If you read any introductory physics book about energy, they all will say energy is hard to define. Right? That's always how the chapter starts. It's really, we can't really define it in any good way, which is sort of ridiculous. There's a technical definition of energy, but when you're teaching intro physics and just learning it for the first time, it is a little bit hard to define. Okay? So everybody who's ever taught intro physics, I don't like to generalize too much. Everybody who's ever taught intro physics has struggled with how to define energy. And everybody goes, wait, I have the ultimate analogy. I have it. Energy is the currency of physics. Oh, and you think I'm going to be famous for this analogy. Currency meaning money. Okay? You all know what money, Venmo. Energy is the Venmo of physics. Okay? And the analogy is if you have a lot of Venmo, you can do a lot of stuff. You can make things happen in the world. And if you don't have much Venmo, you can't do anything. That's the idea. If the system has a lot of energy, it can make a lot of things happen. It can make a lot of changes. And if it doesn't have any energy, it can't really do much. Okay? I'm going to be famous for this analogy that I finally thought of. And then you keep reading the book, and everybody thinks of this analogy. Right? This is the analogy used for energy. Some books, I have one book that I swear to God goes on for like 3 pages of this analogy. It's like there's like a central bank and a Fed, and there's like all of its currency manipulation. It just goes on and on. It takes it way too far. It's not worth going that far. But it is the idea. That's the only simple definition we have. So what we do then is we go straight to the first kind of energy. We don't get all high-minded about it. We just go straight to kinetic energy. And this is like one of Newton's laws. If you've taken any physics, and if you haven't, that's okay. But if you have, you know the definition of this. It's the energy, the second word is a word that I can't define, of motion. When something is moving, it has kinetic energy. That's the idea. It's in a new unit. It's in kilogram, meters squared, per second squared, or joules. That's O-U-L-E-S, which is J. Joules. Named after Mr. Joule. So the idea is it's the energy of motion. The more motion you have, the more energy you have. So first, let's get that sort of in our head. So this is a system I want to interact with, and I want to make a big change on this system. And I'm this system with my cart. So if I don't have a lot of motion, I have a low amount of motion up like this. I'm not going to have much of an effect on this thing. Nothing. Very low energy. We want to do it with high energy. Does anybody want to join me on the cart and do it with high energy? That will lead to madness. Okay, here we go. This is high energy. High energy. I made a big change on the system because I was moving fast because I had a lot of kinetic energy. So let's look at the formulas for energy. Okay, there's translational kinetic energy, which you just witnessed. My leg got caught in a little angle and I nearly broke my femur, which has never happened before. K equals 1/2 mv squared. So not only does it depend on motion and moving fast, it goes as v squared. So as I really start moving, my kinetic energy goes way up. This is the one that you learn about all the time. And this is for translational, something with mass m and velocity v. Okay, but here we've already done rotational motion. So we can go ahead and write down the rotational formula. There is also rotational kinetic energy. And that is K equals, and remember all the rotational formulas are just like the translational formulas. You just substitute the rotational values. 1/2 is the same. The rotational mass is the moment of inertia. The rotational velocity is the angular velocity. So it comes out the same. So say you have a disk, mass m going around at omega, 1/2 I omega squared. And I want to be clear, translational and rotational kinetic energy are the same thing. They're just energy. They're all in joules. We could go through this unit and say, what is the unit of I, of moment of inertia, kilogram, meters squared? What is the unit of omega? Radians per second, radians squared per second squared. Right? And you say, oh, but radians aren't real. So kilogram meters squared per second squared. Same unit. And then if you broke this down into individual little points, it's really just little masses moving in V. And if you added up the 1/2 mv squared of every little atom in this disk, you get the same thing, 1/2 I omega squared. You can derive what I is this way. We just didn't do it that way. Okay? Okay. Let's do a few bullets on this one about energy. Okay, here's some bullets. I've decided to make my bullets actual bullets like that. One, here's the good news. It's a scalar quantity. So this one is easier than momentum. Momentum was a vector. Never sneak up on it from behind one lecture. Momentum was a vector that made it more difficult to deal with, vector quantity. This is just a scalar, so that's good. Another thing about kinetic energy is it's always positive. These are both about kinetic energy, not necessarily just energy. Okay? So this is kinetic. This is actually both. Energy is always a scalar. Here I'm just talking about kinetic energy. Always positive because the v is squared. So even if you have a velocity backwards and v is negative, you're going to square it. You can't possibly have a negative kinetic energy. This is related. V and omega are essentially just magnitudes. And the direction is irrelevant. So here is something, a mistake. Let me get a look at you guys. A mistake 27% of you are going to make on the exam. Ready? Based on just your general look, I'm going with 27%. Is you're going to do a problem, and you're going to say, okay, a mass takes off at V naught. I want to do this with energy. The first thing I'm going to do is calculate energy in the x and energy in the y. 1/2 mvx squared and 1/2 mvy squared. No, don't do this. Okay. Energy does not have directional components. It is a scalar. The only way to start this problem with energy is to say that the energy has nothing to do with direction. 1/2 mv naught squared. Do not do this. People will still do this, people that don't come to lecture. You do not break it into components. You just stick the magnitude in this formula. It's because it's squared. We can't break it into components that add together because it's squared. It's not proportional to V, it's proportional to V squared. Okay. And then there's this idea that energy is constant. It can't be created or destroyed. And that is true, except for one thing. Is K, kinetic energy, depends on your reference frame. So if I see something moving by me, I say it has kinetic energy. If I start moving with it, I say it doesn't. So when you say energy can't be created or destroyed, BS. I can destroy energy, I can just move with the object. There, its energy's gone. Okay? So energy can't be created or destroyed within a frame of reference. It has to remain constant within one thing's frame of reference moving. Technically it does. Sometimes people just wonder, wait a minute, if I'm moving with the object, doesn't K can't be suddenly zero? The answer is yes. The whole thing we'll talk about later about conservation of energy, that's from a specific reference frame. Okay, that's big picture on kinetic energy. Now, we're going to calculate a couple. It's a pretty straightforward formula, but just for fun, we're going to calculate it. And I need somebody to be the timer. Who here is into steampunk and wants to admit it? No. Is anyone into steampunk? No steampunk doctors here? Okay, who wants to use this timer that looks kind of steampunky? Look at this. 1912. It still works. Look at that. There you go. Come time. And okay, we're going to calculate my kinetic energy. Just time me from here to here, which is 3 meters.
Wait, hold on.
Oh yeah, you hit it once to go, and then you just read it. I don't know how to read it. It's in like old-timey English. Can you read it? Okay, good. Here we go. I'm going to start on the carpet and start here and the other end of the bench go over there. You ready?
And here?
Just from this end to that end. You ready? Go! Stop.
Okay.
What'd you get? I can't read it. 1.81. Now wait there, we're going to do another one. Okay, what's my kinetic energy then? 1/2 mv squared. So if this were a problem, you'd have to estimate my mass. The card is heavy, 80 kilograms. But now V, I went 3 meters in what? 1.81 seconds. So it's just the normal V you're used to dealing with squared. Okay. I didn't work this out ahead of time because I didn't know what would happen. Okay, so I don't know. It's like a little less than 2 squared, 3 over 2, 240, about 120 watts. 120 joules. I get 120 joules, but I did it quite wrong. Okay, so we just did that. Well, that was fun, right? Let's do rotational. Wait, hold on. We're going to do rotational now. Let's do rotational. So this is like a rotational thing, and I'm going to do the skater trick to get my speed really high. Okay? And once my speed is high, calculate or measure 2 laps around. Okay, I'll see you, and then start, and then 2 around. So first, let's just get a little speed going here. So the reason I can do this is angular momentum, which we didn't cover, but that's okay. Okay. Okay, go ahead and do 2 laps around. Let me know when you're done before I vomit.
I'm done.
Are you done?
Yeah. I don't know if this was 2 or 3. I think it was 2.
2.11 seconds.
2.1 second.
Okay. Okay, so we're going to do K equals 1/2 I omega squared. So this is just a little bit of practice. Okay? 1/2 is 1/2. What is my moment, though? Now, we don't want to make you do approximations. That didn't go well on the first exam, right? But my approximation, I would say, is my moment, if I'm roughly a disk like this, is, what was a disk? 1/2 mr squared. Right, no, we're done. That's the last one. 1/2 mr squared. Right? So there's a half due to the energy formula. There's a half due to 1/2 mr squared. My mass, oh, I don't have the card. Oh, but the chair's heavy. 80 kilograms. And then the radius, if you approximated me as a disk, I don't know why I keep doing this, but would be like this far. What is that? 20 centimeters, 0.2 meters. Mr squared. All right. So there's I. We just calculated I. And then omega, let's see, I went around twice in 2.1 seconds, or well, let's say 3 times. 3 rotations in 2.1 seconds. Okay? So 3 rotations, you'd replace that with how many radians per second? 6 pi radians per second. Each rotation is 2 pi, so 6 pi meters. So you do all that and you get a number. And I didn't even estimate it. It'll be less. Well, I don't know. I don't know what it'll be. So I'm just going to go on. If somebody has the number, shout it out. Shout it out. I didn't throw up this year, so that's an improvement. I didn't throw up. You guys are too easy. Okay, so that's just a simple, it's a straightforward formula, straightforward calculation, but you got to remember how to calculate these things if you have a homework problem with rotation. Let's look at sort of a hypothetical problem we could do that would be kind of fun, is let's imagine the kinetic energy of a rolling disk. Kinetic energy of a rolling disk. Right? So we thought about rolling a little bit when we did rotational energy. You have a disk with mass m, radius r, and remember its center of mass went forward at v, but at the same time it went around at omega. That was kind of the idea, right? It's not bad. Okay. So let's think. Let's compare. What's higher? Is it K translational or K rotational? Classic potential multiple choice on an exam, maybe. Okay. Well, we just calculate them with the quantities we're given. There's no numbers, but you can use symbols. So K translational, well, we have that one. It's just 1/2 mv squared. We have m, we have v. There's nothing to do. 1/2 mv squared. And then K rotational is 1/2 I omega squared. So you say, well, I don't know, because you didn't give me any numbers. Which one is higher? We don't know I. We don't know omega. Well, we could get I, though, because it's a disk. And it's mass m and radius r. Okay, we can get I. 1/2, don't max that up with the 1/2 in here for a disk. mr squared omega squared. Okay, so now we have it both in terms of m and r. Doesn't matter for one, does for the other. So you still don't know which one's bigger, do you? No. How are we going to figure out which one's bigger? See, this would be the part where can you see it? Can you get the connection? Can you think back to the first part of the class? There's a connection between the two. Remember, and the problem would have given you hints and been real specific. It's rolling without slipping. Rolling without slipping. Without slipping means that the translational velocity is the same as the velocity of the edge of the disk. Right? The translation of the whole thing is the same as the tangential velocity of the edge. Or that formula you may recall, v equals omega r. Remember doing that? Oh, God, I didn't have this thing on. When will the PHYS problem be uploaded? Very soon, later today. Do you have to square that omega? Yeah. Oh, did I leave it off? Squared. Oh, yeah, that's okay. Now you'll shout out the number now that you've confirmed. Okay, so now if we basically realize this, then we can say, oh, okay, now we can actually get everything in terms of m and v. 1/2 mr squared. Omega is v over r squared. Okay, so now you see what's going to happen is the r squareds go away. This is squared there. So you get 1/4 mv squared. Right, so rotational is 1/4 mv squared. So the answer is translational is the winner. Okay, translational is bigger. Thought they engineered it enough, but they didn't know what they were doing. Let's see. So now, am I telling you that for everything you ever do in life, that translational kinetic energy will be twice rotational? No. Okay. So you could have this object. Let's imagine this thing just floating through space, no gravity or anything, and say it's spinning like this really fast, right? And it's barely rotating. Then its rotational is probably bigger than its translational, because there's a lot of energy in the rotation and very little in the translation. Okay? Or you can imagine it's translating really fast, and it's slowly rotating like this. Oh. Now its translational is bigger than its rotation. The only thing that let us be specific in this case is because we were rolling without slipping. There was a relationship between the two. But I'm not trying to tell you that these are like inherently coupled to each other. They can be any value they want. It's just rolling is a special case where one is always a certain fraction of the other. And it's not even always a factor of 2. Right? That was because this is a solid disk. What if it were a sphere? Ooh, then that would be 2/5. What would that do? I can't do it in my head. I guess I could. So that's just an example, like a quickie little symbolic problem we found out to do. We could ask you that for a sphere. Let's say that'll be on the exam. I don't know. Okay. So that is the most I can possibly talk about work, okay, for what we're doing so far. Now, I'm sorry, that was the most I can talk about kinetic energy for what we've done so far. Now let me look at work. As you can imagine, there's more than one thing going on than just kinetic energy. Okay. So here is a further analysis. And this one is going to make you famous. This is the one that I've come up with. Oh, but it's gone out of fashion. Work is the ATM of physics. Okay? Physics. It's how you exchange in joules. Okay? So you know what an ATM machine is? Automated teller machine. It's when you can get this cash. Right? This is real money. This is what it looks like. Look at this. Brushes are way overpaid. Look at that. 4 singles. This is where you get cash. If you want the true 80s, SID 80s experience next year, I went to college before there were even ATMs everywhere. Forget not having other things. There were no ATMs. So on Friday, you went to the grocery store. Have you written a check before? You write a check and you'd write it to cash, and you'd give it to the grocery store person, and they would give you cash. And then you had cash, and you had fun on the weekend, and when you ran out of cash, you were done. And then that was the end of the weekend. That was over. You had no other access to your money back. You couldn't use credit cards at bars back then. They didn't. Well, the grocery store was like a bank, and they had tons of cash. I mean, there was a special aisle for cash. Like, there's a place to buy your groceries, and then there's the window where you just get cash. Yep. So SID 80s next year, do that on Friday afternoon. Then you have the legitimate experience, not whatever you do. Okay, so ATM of physics. Let's see. What we got to do is, this is the basic idea. We're going to exchange. So to do work, you push with force F through displacement R. Force F through displacement R. Okay? So what we're going to do is give you sort of 3 versions of the mathematical definition. And we'll do a little example for each one. Because it's kind of like torque. There's a few ways you can calculate it, depending on how difficult your situation is. So let me just show you all 3. So first is, remember we physicists like to say in general. Okay, in general is Latin for, don't write this down. Okay, so in general, the work is the integral between 2 positions, say R1 and R2, of the force dotted with the change in position. Okay. Now look a little bit, remember impulse was how the force is times the dt, how the force is a function of time integrated over time. This is the force as a function of position integrated over position. So if you have a case where a force varies, you actually have to use the integral. Okay, we'll maybe do 1. Okay, usually though, you might have something more like this too. If your force is constant, then you don't have to deal with integral. Right? If it's constant, then the integral of dr is r. So then you get the work is F dot dr. So you do have to deal with a dot product. Okay? So I think when we did vector intro, I don't think we did dot and cross product. I think the plan was to do them as we go. Okay? So this is just a way to multiply 2 vectors, and dot product is the one where, say you have an object that goes through a distance r, but your force is in the same direction, so you're pushing like that. The real answer is you just want the component of the force along r, and that's what the dot product is. Okay? Dot product gives you a scalar, right? The dot is 2 vectors make a scalar, and it's just the component of the parallel component of the force parallel to r. And this is not a detail. The whole point is it's not. Okay, so you can write it that way if you're in formal vector world, or you can write it this way. Remember how for torque we had like the perpendicular component? You can also see it written like this. It's just the parallel component to r. Take the force, find the component parallel to r, multiply that by r, the displacement r, and that would be it. So that's a little bit easier to deal with. Or if you're in polar vector world, you could write it as the magnitude of the force times the magnitude of the displacement times the cosine of the angle. The definition of dot product is 2 vectors, magnitude, magnitude, cosine. Going from F to R. Okay, so in some problems you would need to do that. Right? You might not be pushing exactly along the force. And then number 3 is the best, is when the force is constant and parallel to the displacement. Oh yes, then it's just F. It's constant, you have to do the integral, they're aligned, theta is 0, cosine 0 is 1, the component F along R is just F, F1. These are all the work. Okay, so let's look at a few cases of using colors. So let's imagine, we're going to do them in reverse order. Let's do the easiest one first. Let's do example 3. You got a mass on a table with friction mu k, the kinetic friction coefficient. You're going to push it with your hand at constant speed. You're going to push it from 0 to d. Okay? So I made it a little harder than just saying Fr. Because we want to see, just make this a little more interesting, instead of just giving you F push, let's figure out what F push is. Just to make it more interesting. Or let me give you F push and then we'll solve it. So you push with F push over that displacement D. And the question might say you push at constant V. So it's moving at constant V, that's why we use the kinetic coefficient of friction. Push at constant V from x equals 0 to x equals d. So you can say, what work do you do when you do this? Well, you go back to the simple formula. F is constant, F is along the displacement, there's the push force, there's the displacement vector from 0 to d. They're parallel. So you say work equals F push times d. And you're kind of done. But since we spent 8 weeks on all this other force stuff, we could probably do a little better. If I push something along a table at constant velocity, I must be balancing what force? Friction force back. So we could actually calculate FP. We could say FP must equal, or well, be the opposite of, okay, the magnitude of FP must equal the magnitude of the kinetic friction. So I think we call that little f with a k, maybe? Maybe big F with a k. Those have to be equal if we're not accelerating. So we could plug in and make it a little more technical. Right? And we know that because we're at constant v. I won't go back and do all the Newton's laws here. But we can say that is mu k times the normal force. Okay, but the normal force in y must equal weight because we're not moving at y. So it's mu k mg. mg. So just to make the problem not a complete FD, right, we might do something like that to make it a teeny bit interesting. So anyway, that's example using formula 3. Let's do example using formula 2. We'll do this with numerical. What if we had a surface and a mass, 5 kilograms, and we're pushing down with 10 newtons, 20 degrees from the normal, like that. And the same question, we go from 0 to 2 meters. What work do we do? How much work have we done? So you might look at it and say, well, we need mu to figure out the friction force to make sure it balances or something like that. But we don't, because I didn't say it was at a constant speed. I just said we're pushing like this and it's going. It might be accelerating, might be going constant speed. It could be decelerating? Sorry, give me a second. Yes, it could be decelerating. You have an initial velocity that's slowing down. All we know is you're pushing with a constant force from 0 to 2F. So we don't actually care about how all the forces balance out. All we need to know is the external force we apply and how far it goes. So this is the case we need the second formula. Because F is constant, but they're not parallel. So it's just a dot product. There's that vector. So we say work is the F dotted with basically the R vector, which is 2 meters from one to the other. So to do the dot product, we just say it's the magnitude, 10 newtons, times the magnitude of this vector is 2 meters, times the cosine, but it's got to be the cosine of the angle between them. So it's not necessarily the angle you're given, right? So in this case, I would just draw them tail to tail. There's R, there's F. All right, and then you do your high school geometry here, and that's theta, and that's theta. So this must be 90 minus 20. So the actual angle between the two vectors is 70, cosine is 70. That's what you got to do. And I get 6.8 joules. 6.8, those of you that can't see. You could probably do that. Okay, so that's using the dot product. Be careful with your angle. Just like in other things that we've done. Let's do the third one. The third case is the hard case. Oh dear. The third case is what if the force is going to vary? So here we have constant push forces. Oh, the hard case would be, what if we had a spring pushing the mass? Spring constant K, mass M. The natural length is always at the origin. It wants to be there. We have pushed it back. In this case, it would be the back that matters. Minus A. Right? So the work from minus A to 0. So the natural length is here. I forget if that matters or not. Let's say that's the natural length of the spring. So here you'd actually have to do the integral. Oh my God, let's do the integral. So the work equals the integral from where it starts, minus A, to where it goes, 0. There's our limits. We're pushing it from here to here. Times the force, and the force on the mass is minus kx. Right? So you can write it down as Hooke's law first, and then you can go check it and say the force on the mass. If I go to negative a, and I plug negative a into minus kx, I get a positive force, and that's correct. Okay. Minus kx and then dx. There's no dot product because they're in the same direction. Right? So this is the hard case, but where they're aligned, so we don't have to do the vector part. So we just do this real quick. This is minus 1/2 kx squared from minus a to 0. Right, like that. Lost the minus sign. Right, and then you evaluate that, and you just got to be careful. Plug in 0 minus, plug in negative a. Minus 1/2 k negative a squared. Minus 1/2 ka squared. So that's how much work you did on it. It came out positive. That's good. Because we did speed it up. So it gained kinetic energy. That's getting into conservation, which we'll be talking about. Okay. Now, one more thing on kinetic. We'll do it after the break. Take a break and then talk more about kinetic. Or no more. Yeah, so that's okay. I want to go back and do it all again, but we are moving with constant velocity. We do have 240. go. So I have a third example of a force causing motion, and we need to calculate the work. It is a miniaturized. Speaking of the 80s, anybody here about miniatures? There are things in the 80s you don't want to know about. Okay. Your mom, your grandmother did miniatures. Ask her about it. Okay, so here is a miniature version of the big conical pendulum. I didn't want to get it out because, you know. Okay, so it's going around, right? And let's remember why it goes around and what the forces are as it goes around. So we're going to answer the question, does every force that causes, I'm going to put causes, motion do work? And you can probably guess the answer because I have posed the question. Because the way I'm speaking, does every force that causes motion do work? So let's see if this one does. So what's happening? Remember the conical pendulum, the mass was here and it goes around in a circle, and the thing responsible sort of is the tension. And we had to balance the forces, let's see, we had to have the tension this way, and its y component balances gravity. Right, that balances its weight, and what was that component doing? That's the centripetal force. This is the centripetal force. All right, so it's basically, it was like Tx equals mv squared over r, or something like that. Right, where this is r. Okay, think back to that lecture. I'm sure it's all crystal clear. Okay? So the question is it doing any work? That's what we want to ask. We can also look down. We can say, okay, let's make this even simpler. Just imagine a mass going in a circle here of radius r. Right? It's tied to some string that has some tension T, pulling it around. It might be easier to see this way. How much work are we doing? Okay, let's go to our rules. Let's see. Is the force constant? Well, it's constant magnitude, but it's changing direction, so it's not really constant. So let's go ahead and write out the full thing then. The work is equal to the integral from position 1 to position 2 of the force doing the pushing dotted with dr, the change in the position. So here, let's free body diagram this real quick and look at the thing and say which way is the tension? That way. Which way is dr for any little instant in time? Dr is like dx, it's like ds. It's the change in position, it's this way. So what is the dot product of those? 0, right? They're perpendicular. Cosine of 90. Cosine of 90 is 0. So this is 0 because the force is perpendicular to dr. So every force pushing something around doesn't have to do work. It doesn't have to speed something up. And if you think about this thing going around, the tension force of this is never going to speed it up. Right? What's sped it up? Is sped right? The English major. I know that's what you work on grammar as well. What sped it up? My hand sped it up. I did a push force to do the work. And which way did I push it? In the direction of its motion. Right? That's sped it up. There I did work. It was positive. But the tension force now isn't going to speed it up. Right? It's the wrong way. It's always perpendicular to the motion. That's a hallmark of circular motion. Okay? So just keep in mind, everything doesn't do work. There are forces that don't do work. Or if two forces balance, then the net force doesn't do any work because there's positive work and negative work. We'll get to that in a minute. You can have negative work, believe it or not. Okay. So now what we're going to do is connect work and kinetic energy. And it's sort of, we've kind of been doing it, right? I've kind of been calculating work and talking about it speeding things up. But now we want to do it a little more carefully with a theorem. We love theorems. Work, kinetic energy theorem. We've got to decide formally how are these two things connected to each other. Okay, so, and we got to get into systems, kind of like we did with momentum. Okay? External work. We've got to talk about what external work means. On a system, external on a system equals change in kinetic energy. if we're going to write that, there actually isn't. If we're going to write that as a formula, right like this. The work that we've been talking about, F dot dr, this system pushing something, we'll put an ext there. Make it clear, we mean something pushing. So before, like the cart, I didn't get the cart out. When we pushed the cart was a system, and I pushed it with my hand. Equals delta K, the change in kinetic energy of the system. So that's basically the work kinetic energy. Everything we did with work, we were doing this. We were speeding things up. We were pushing on things to speed them up. Okay? You can also write it there. So when we get into changes, there's a lot of way to write them. I'll do it more next week or Thursday on when we get to potential energy. Oh, my watch is here. That's right. Will there be class the Tuesday before Thanksgiving? Of course. Why would there not be class? Can you explain that tension equation again? Sorry, I didn't have this on and I missed it. Why is dr related to tangential velocity on angular? Because it is in the tangential direction. Right? The direction this thing goes, it's always moving tangentially. It's never moving radially. Okay, sorry, I'm not catching this. So, this you could also write, if you wanted to, as K final minus K initial. So when we get to conservation of energy on Thursday, we'll spend a lot of time talking about how to think about differences, how to keep them straight. So that's just your first look at it. Okay, so here we're going to push the cart. Here we go. So the cart here. We're going to do the whole thing. So we've got a cart like this that rolls on the surface. Okay, so the cart is the system. So you got to decide what's the system. Is it the table? Table in the cart, the hand. Right now we're saying it's just the cart. So I'll put a dotted line on it. Just the cart. And it helps that it's a frictionless surface, frictionless cart, so it doesn't really interact with the table. U equals 0. Okay, no friction. Perfect wheels. Now I'm going to have a hand and I'm going to push it like that. Hand applies, and it must be external because I'm not part of the system. External force. So of course F push. So what's going to happen? Here's the hand. Wait, let's go the same way. There we go. I don't want to confuse you. All right, here's the system. Here's the hand. I push. It speeds up. I pushed from one position to another position, and it sped up. So let's see if the signs make sense. It went faster. Okay. So the work external. We're not going to recalculate these, but I basically just did it a bunch of times. Is the external work positive or negative? Let's think about the vectors. I'm going to push it from here to this lost little chain that somebody hasn't picked up yet. Okay? I'm going to push from there to there. Which way is the displacement vector, the delta R? It's that way. I'm going from here to here. I can draw it on here. There's the displacement vector. And here's the force. Same direction, right? So F dot R, so F is parallel to R, so it's positive. Okay? If the work external is positive, then what is the change in the kinetic energy of the system? Positive. That's an equation sign. That means these must be the same. So what does that mean? Well, that means this is positive, which basically means K final is greater than K initial. What does K final greater than K initial mean? Well, the mass didn't change. Did 1/2 change? 1/2 didn't change, so the velocity changed. The velocity increased. If 1/2 mv squared, and the final was bigger than the initial, then it sped up. And sure enough, there it is, speeding up. So as I push it, it gains kinetic energy. That's really all this is saying. The only tricky thing about it is it's keeping up with external, what the system is. And it's mostly intuitive, but in some problems, it's not as intuitive. For a rotational version, I don't have one here, but if I had a disk and I pushed it, right, the disk would have 0 omega at first, 0 angular acceleration. If I pushed it, I'd apply a torque. Okay, I would apply a torque to the disk, and what would it do? The disk would speed up. And the disk would gain kinetic energy. Oh my God, we could do all this rotational, but here's why we don't. Are you ready for this? Let's do equivalent things. Work for translational is the integral of F dot dr. What would it be for rotational? As I apply a torque to the disk, force is torque. Torque dot, what do we go through? theta, d theta. Oh my God, I don't want to get you guys through what d theta vector means, so we're not going to do that. Let's just keep it translational. Because then you have to acknowledge that all those torques and angular rotational things were vectors, which they are. We didn't get into. So we're just going to keep things mostly translational when it comes to this motion. But you'll see on the homework, we'll try to make some rotational stuff. Okay. Okay. So now here's something about signs of kinetic energy and work. Okay. Let's think about signs. What have we said so far about signs? I think the only definitive thing we said is that K, kinetic energy, is always positive. Can anybody think of an exception to that? One exception. Outside the box mathematically, what's the exception? Zero, very good. Now we're starting to get along. It's always positive or zero. Okay. But W can be negative, work can be negative. Right? So the force, if the force slows something down, I'll show you in a minute, the force can be one way, the displacement can be the other way, and you get a negative work. So if you have a negative work, how can K always be positive? And the answer is because it is the difference of K. So if we're thinking about signs, K is positive, work can be either way. It is equal to delta K. So K is always positive, kinetic energy is always positive, but it can decrease. That's the idea. K can go down. So in most energy problems, you're always working with differences. And differences can always be negative, even if the value has to be positive. Okay? My number of whatever is always positive, but I can have it decrease. So let's do a problem that uses this idea. Okay? Let's think about this problem. Here we've got a mass M approaching a spring at V naught. And here's the spring. Sitting here innocently, its natural link, we're going to call that the origin on this x-axis. And we're going to say, how much does it compress the spring? All right, it's flying in, the spring is clearly going to push back and stop it. How far in does it go? So I'm going to write spring stops mass, how far? So how far does spring deflect? You could do this with Newton's laws in kinematics, with F equals ma. In principle, you could. You'd say, I just need the acceleration. I know I have v naught squared, or the v final squared, I have v initial squared, plus 2ad. So if I just plug in the acceleration, I'll get d. But acceleration is not constant. That's the problem. This is not a constant acceleration situation. The spring's force depends on position. So you can't even integrate it with respect to time. Because it ends on position. So this would be a hard problem you have to deal with. Differential equations and stuff. Or you can do it with energy. Right? Let's do it with energy. Let's say the work that the spring does, F dot dx equals delta K. W equals delta K. And let's make the system the mass. The system can move. It doesn't have to sit still. Okay. So let's see. So we would say, okay, let's do the integral first. Let's see. It's the integral. The thing is going to go from 0 to d. From 0, the thing we're looking for is in the limit of the integral. Oh my God. A little teeny bit of calculus-based physics here. What is the force on the mass? Well, it's minus kx. Hooke's law. So write it. Minus kx. And now check it. If we go to positive x, do we feel a negative force? Yes. Okay, you did it right. Very good, Jason. Thank you, God. I just want some God. And then we say equals what? Kf minus ki. Oh, no. Minus ki. And then you just go to chapter. The calculus part, the fun part. Minus 1 half kx squared. Minus 1 half kx squared from 0 to d equals, what is k final?